All right. So what we learned on Thursday, for those of you who are in the regular section, who could summarize what we learned on Thursday? What was sort of like, what was the tricks that our triangle learned? Yes, Quinn.
When the triangle was put in the context of like a graph, it got a lot of like new abilities of what it could do. And when you push it like you can push that angle all the way around, like, and into any quadrants, and you get like similar but different triangles that are like reflected.
Yes, exactly. So if we take a triangle and we anchor it at the origin, it's sort of like once our lonely triangle floating in space, it reconnects with its origin, it finds its home. All of a sudden, that allows it to unlock a whole bunch of additional power that it didn't know that it had. What I've started out with here today is also the coordinates of this point that is the terminus of the hypotenuse. Yes, the end. Boop. Yes, the terminus. The end of the line that starts at the origin. And so since these are xy coordinates, that means that this is 4 times the square root of 3, and this is 4. In other words, we can see now that when we know the coordinates of the peak of the triangle, we also know the lengths of the leg sizes. Okay, now I'm hoping that for somebody in the class, this pattern is cueing you in as to what the length of the hypotenuse has to be. So explain and state why. Yes, Miles?
2. Wait, no.
You're heading in the right direction. 8. That's right. And why 8?
Because the opposite is half of the hypotenuse.
Yes, when this proportion
When
is in
that
effect.
proportion.
And what is the measure then of this angle going to have to be? These are the proportions of which triangle? Yes.
36.
Oh, no, go ahead, Miles. You got it.
Are you sure?
Yes.
Okay, 30, 60, 90 triangle.
So, that's right. So this is a 30, 60, 90 triangle. And it's one where here, this angle that we have next to the origin, this is the one that is 30 degrees. What is that?
I think it's someone's tapping. Someone's tapping their foot.
Oh, somebody's tapping their foot?
Can we throw a chair at the ceiling?
I mean,
If someone is doing that,
yeah,
if you
if you don't mind missing this part
No,
of the review, yeah, then go ahead. Thank you, Ollie.
You're anxious?
ceiling chair
Get
works
over
just
it.
fine.
That's a little drastic.
I mean, I hit the broom, top of the broomstick to get my noisy upstairs neighbors to stop
Yeah.
walking like elephants.
We're
That's what they were doing.
okay, so we're gonna refocus now on this, and we're not gonna throw furniture at Renaissance School. I know that's not in the handbook because it really didn't think that it needed to be, but we're not gonna do that. Okay, so right now then, let's Francesca, we can think about the hypotenuse now as sort of being on a hinge here at the origin. So we can think about just, the hypotenuse can rotate down to create like a shallower triangle. It can rotate up to create like a taller, narrower triangle. But if we have this triangle and it's just sort of sitting out in space over here, and it is not anchored at the origin, and we think about just moving this hypotenuse up, for example, and creating this taller and taller, narrower triangle, what's the absolute biggest that this angle could get?
It could get to 89.
Yeah,
89 degrees.
yes.
Because
Or 89.9.
89.9999. Because it just because it just needs to be as long as the two angles add up to 90 degrees.
Right. I mean, because if we had two 90 degrees, now all of a sudden we kind of have like a hippo foot.
But then the triangle would basically be invisible because it would be so.
Right. So we could think of like this tall, like the height of the triangle, like eventually coming up just to match on top of the hypotenuse. But we can't create a triangle with two 90-degree angles. So this can keep going towards 90 degrees, but it can never get to 90 degrees. All right. Well, if we go the other way, and we keep making this angle here shallower and shallower and shallower, and so we're getting a flatter and flatter, flatter triangle, what's the smallest that this angle can get down to?
If I get this wrong, so alright, is it that simple of an answer that I'm thinking?
You're definitely overthinking it.
I think
What's our I mean, so we're just
Well, I mean, like,
thinking
What's the closest you can get to zero without getting to zero?
yeah, or like 0.0000001, like we can keep going, but we can't get all the way to zero.
Oh, okay.
Yes.
Oh, it's like the what are they called?
Decimal.
No, it's like the lines that go.
Oh
forever.
yeah, it's like
Can
asymptotic.
Never,
Yes.
Yeah, asymptotes. The
Yes.
lines that go but can never touch the line.
Right. And so our triangle here that's just sort of like floating out here in space, this angle is actually very limited. We have 360 degrees in a triangle, but this angle can only be between 0 and 90, and not even including 0 and 90. So that's a pretty huge limitation. However, when we anchor the triangle here at the origin and we think about the hypotenuse being on a hinge, we can actually just go ahead and rotate it. We can just keep going past the y-axis. And in fact, if we can actually keep going, and we can stop here at this point. And in fact, now it's like the triangle, it's like it has gone through the looking glass and it can now see its reflection. Okay, we've introduced a couple of things here that we need to label. This direction of the x-axis is now always going to represent 0 degrees. So as we lift the hypotenuse off of the horizon, this is the angle that we are measuring here at the center, and this is 0, and then we start going up into angles bigger than 0 here. All right, straight up and down here, vertical then. If this is 0 degrees, how many degrees is this vertically? Yeah, Miles.
90.
Yeah. So this is 90. And if we keep going, and now we're going the opposite direction on this horizon, how many degrees will that be?
Negative.
Well, this is the negative direction for this side, but in fact, if we go past 90 degrees, like how much is this approximately?
92.
There you go. But if we keep going all the way, so we're going the opposite direction.
180.
That's right. We've done a 180. We've turned it around.
So what's the next? Wait, circle.
Yeah. So that means this is 270, and if we just keep rotating like a clock kind of all the way around, we come back here to 360 degrees. So we can think about, we've rotated, we've gone past the 30, past the 90, but if we've created an exact reflection by stopping the hypotenuse right here, how many degrees then must this be?
Well, it will have gone. It reflected across the x-axis.
Yeah, this triangle is a reflection of this one, but it's
Maybe
because we've
180.
moved the hypotenuse. We went up to 30, we kept going past 90.
I think it went 180.
So if it were 180, then it would be going, then the hypotenuse would be right here. Because 100,
Oh, okay. Then it would be 90. What's between 180 and 90?
150.
why 150 miles? I'm seeing hands. I know, but I wanna, because you guys have already seen it.
Are we the only people who haven't seen it?
No, there were other people who weren't here.
135.
135. Okay, Ollie, what do you say and why?
120.
120. Why?
Yeah. Oh, that's because 30 plus 90 equals 120.
So if we've created a reflection, is this 30?
135. I agree.
Me too.
Yeah, I agree.
Okay, so 135, that would be 90 plus 45 degrees. How much would that leave here?
Wait, there's 60.
Right. So so I heard 120, which is 90 plus 30, but then that would leave 60 here. Is that an exact reflection of this? No. If we do 145, if we do 135, then does that leave?
Wait, no, no.
Then that
it's
leaves
150.
45 here. So why 150 then? we're getting it. I see that we're getting help from phoning a friend here, but somebody needs
because
to
it's not
actually.
in the half. It's not to scale.
But we know it has to add up to. We know it has to add up to 180.
I wasn't. I was just guessing.
So there. Well, but let's.
Just kidding. I was.
But let's see if we can logic this out though. If we've stopped to create an exact reflection, how many degrees are right here?
30.
So where do we have to stop to leave 30? 150, that's right. Because 150 plus 30 is 180. So to create this 30 degrees here, we have to go 150 from 0. Very good. All right, and then that means our height here is still 4, but now actually what's the measurement here of the base of this triangle? Given that we're now on an XY coordinate plane.
Would you repeat that?
Yeah, can you repeat the question?
So,
Can you just like repeat the question?
yes, so we've created an exact replica. The height is still 4. But what is actually the length of the base of this triangle now?
It's still 4.
But given that now we have anchored this triangle in an XY coordinate plane, which has directionality,
Oh, negative 4.
right?
Is the hypotenuse negative 8?
The hypotenuse is still 8.
Okay.
Because it's diagonal, which means the slope is still the same, right?
Well, the slope is actually reversed because this is positive and this is negative. But because we get the hypotenuse by squaring and adding the lengths of the legs, this is always going to be positive. Yes, Quinn.
I have like a really quick unrelated question.
Yes, go ahead and hit me with a quick unrelated question.
What is the terminal side of an angle?
This is this is the terminal side, the hypotenuse.
Okay.
Yes. Good.
What's the like definition that I can write down, like of, like not a definition, like what can I write down in words, like of what a triangle can do when it's on a coordinate plane?
So that's a really great question. So once now it's on a coordinate plane, before could we ever have a right triangle that had an angle of 150 degrees? No. So one of the things that we can do by anchoring it on the plane is that now we can create versions of triangles of right triangles that have angles greater than 90 degrees. And in fact, we can keep going all the way around the circle. So this trick of anchoring the triangle at the origin in the coordinate plane now has broken us out of the, what does that say, Alex?
I was asking if they're no number. According to no.
Okay, you need to focus on your work. So if your 4.4 is done, then you need to be working on the challenge problems. Because like I said, first what we're going to do is we're going to take some review notes. If you do not need the review notes, you can be working on 4.4. If your 4.4 is done, then you can be working on the 4.4 challenge problems. Once the notes are complete, you'll have the opportunity to work with your classmates. But while we're doing these review notes, because we covered a lot of territory on Thursday, everybody needs to be focusing on their own work. Okay. All right. So one of the things that we have been able to do is to achieve triangles with angles formerly impossible. We used to be limited from 0 to 90. Now we can go past 90 degrees and in fact all the way to 360. The second thing that we've achieved is now we can have a triangle that has negative side length. So by anchoring it in the coordinate plane, now we can have negative side length. So let's go ahead and, so this new framework also requires a couple of additional labels. Because we start out here at 0 and go to 90, this is quadrant 1. But as we continue rotating around the center, this becomes 2. This is quadrant 3. Any guesses on what this last quadrant is?
Cool.
Very good.
Geometry reference?
So let's go ahead and take a look then at one example of what this means in terms of trigonometric ratios. So let's go ahead and look at the sine and cosine of 30 degrees.
Oh, would I have that?
Yes, this is one of our sort of usual suspects. So these should be familiar or becoming familiar. But I'm going to go ahead.
Ah, I tricked you. I did not have it written down.
Okay. Well, then let's go ahead and figure it out. Sine is what over what? Opposite over hypotenuse, 4 over 8. Which equals 1/2. Does the sine of 30 degrees depend on the size of the triangle?
No.
No. All right, how about the cosine of 30 degrees?
That would be square root 3 over 2.
That's right. So it's adjacent over hypotenuse. We've got 4 times the square root of 3 over 8, which simplifies to the square root of 3 over 2. All right. Now let's take a look at the sine of 150 degrees and the cosine of 150 degrees.
What if it's the same?
So we've created a reflection of the exact same triangle, so we should actually expect the proportions to remain the same.
Yep.
And here this is 4 over 8, which does equal 1/2. However, when we look at the cosine,
Negative.
it's negative. So we've got negative 4 times the square root of 3 over 8,
Negative 3.
which is negative square root of 3 over 2. Okay? What I'd like you to do, if you didn't have the chance to do this on Thursday, is find the following. Tangent of 30, tangent of 150, sine, cosine, and tangent of what the angle will be here in the third quadrant to create the same reflected triangle, and sine, cosine, and tangent of what the angle will be here to create the same reflected triangle. You need to find the angles, however, what I will tell you is when we look at all 3 of the reflections of the original triangle, it ends up looking like a bow tie.
Very good.
Okay? So go ahead and work on that if you didn't have the chance to do this on Thursday, and then raise your hand so that I can come have a look. All right. Now, I know that there were questions about the 4.4 assignment, so I'm going to take those next. So yeah, so Cade, which problem did you want us to look at?
The last one,
Which is number,
96.
okay, and Quinn,
25.
25. And is there anyone else who has any questions now that they are working on the assignment?
How do, oh, I'm not looking.
Well, here, because remember, the key was we had to figure out where to stop so that we had a 30-degree angle here.
Right.
And you're going to have to do the same thing here. So you're going to go past 180, but where do you stop
Oh boy.
to create a 30-degree angle here? You can confer with your colleagues on that. All right, so let's take a look at number 25.
Oh, we have to actually label them with what they are.
Yes. All right, so on 25, we are finding the ratios of the 6 trigonometric functions of theta, and we're looking at the angle that is formed by a line. We have y equals negative x. So the first order of business on this one, Quinn, is graphing the line y equals negative x. If we don't remember what the graph of a particular function looks like, the best thing to do is to pick some x's to plug in and then to find out what the y's will be. And a good smattering will include positive and negative values and 0. So what would be some numbers that you would like to plug in to the equation to get the x's you'd like to plug in to get y's so that we can graph the line?
Negative 5.
And we can do maybe one more negative 1,
Negative 3.
negative 3, we want to do 0, and then do a couple positive ones too.
7.
7. Okay. I'm gonna say how about 2. Okay, so if y is equal to negative x, what's negative negative 5?
5.
Yeah. And negative negative 3, and negative 0
0.
is just 0. All right, and then even when I say it now, it gives us the answer. Negative 2 is negative 2, and negative 7 is negative 7. So, three, 0. Okay. So here is y equals negative x. And now we're told to find the values of the 6 trigonometric functions of theta in quadrant 2. So remember that we start here. So where we're going to stop is here because this is quadrant 2. So this is our theta. So we need to find the 6 trigonometric functions of this theta. Does it matter how big we make the triangle in the second quadrant?
210.
Do the trigonometric ratios depend on the size of the triangle?
No, not the lengths.
Right.
Just the proportions.
Just the proportions. So that means we can draw this triangle anywhere we want on this line. The trigonometric ratios will not be affected. So since we already have this point, negative 3, 3, my suggestion is that we go ahead and use this triangle right here to find the ratios. But again, it's not going to depend on the size of the triangle. We could easily have picked, because we have this other point, negative 5, 5. We just as easily could have made the triangle here and still used that. Okay, so if we're going to find the 6 trigonometric ratios, what's the piece that we're missing on this triangle?
Hypotenuse.
The hypotenuse. And so we're going to need to calculate that. So that's going to be 3 squared plus negative 3 squared. That's going to equal the hypotenuse squared. And 3 squared is 9. And negative 3 squared is also 9. And so I'm going to move this over here. So we've got 18 equals h squared. And what's the next step that we do now to solve for the hypotenuse?
Root them both.
That's right. We take the square root of both. And are there any perfect squares that are factors of 18? 2 is not a perfect square. But 2 times what is 18?
9.
Is 9 a perfect square? Yes. Yeah, we've got it right here. So this is going to be the square root of 9 times the square root of 2. And so we've got 3 times the square root of 2 is equal to the hypotenuse. And in fact, the length of the leg times the square root of 2 is always going to be the hypotenuse of an isosceles right triangle.
Wait, will you say that again?
The hypotenuse of an isosceles right triangle. So a right triangle where the legs, the absolute value of the length of the legs is the same. The hypotenuse is always going to be the length of the leg times square root of 2. So that's another sort of usual suspect. Yes, Francesca?
I was wondering if you check my work after I finished the
Yes. That's right. Very good. Okay, so
Did I get
now
the angles right?
you've got the angles right. So everything you've got here is right. So the last thing that I want you to do is to do just a little key. It has SCT for sine, cosine, tangent in each quadrant, and where each one is positive and where each one is negative. So you just have like a little key in each quadrant, because that is not restricted to 30 degrees. Sine, cosine, and tangent are all always going to be positive in the first quadrant, and that pattern that you're seeing of who's positive and who's negative in which quadrant, that will be consistent. All right. Yes, I've got that one up on the board.
Mostly 96.
Okay. So the first thing is this drawing done to scale?
Absolutely.
Because if it were, how tall would that man be?
Very, very tall.
2 miles tall.
Very, very tall.
So
What's all the man?
does anybody still need what is written up on the board here? Okay. So I'm going to carve out a little spot
I don't need all the stuff around it.
over. I'm just going to carve out a little spot over here then
Okay.
for number 96.
I like the bow tie.
Yes. Okay. So when doing these word problems, what's my first suggestion? Draw the triangle. And so in this case, so we've got the man, which really is just going to be like a tiny little point down here. And we've got the plane. We're told that this is D. I mean, here really we're given the ground, we're given the D distance, we're told the altitude. What's the altitude here?
6 miles.
We're told that this is 6 miles. And then
Hey, this is a 36 to 90.
gotcha. So for A, theta is 30 degrees. And so then based on what we know now about the 30, 60, 90 triangle, which is becoming familiar,
It's just twice as 6.
yeah, E is just going to be equal to 2 times 6 miles, which is 12 miles. Let's say that we have forgotten what the 30, 60, 90 triangle ratios are. How could we instead set up an equation that would let us solve for it? What is, if this is our angle,
Sine of 30. So 6 over D.
that's right, so we could say sine of 30 degrees equals 6 miles over D. Okay, now what do we do?
We solve for sine.
Which is like 4.
Well, what are we solving for?
D.
We're solving for D, so how will we know when we're done? What will the answer look like?
D.
Yeah, so we're aiming for D equals some number. Right, but if we're going to solve this equation though and double check our work, what do we need to do here? Because if our objective is to get D alone, right now we've got D in the worst possible place, which is it's in the denominator of a fraction.
Okay.
So how do we get D out from under that 6 miles? I see your hand, Alex.
Cosecant.
Well, is the I would hesitate on that. So you're right. So we could flip both of these. So we could say cosecant of 30 degrees equals D over 6. So you're right. But is cosecant on our calculator?
No.
No, it's not. What was your suggestion going to be, Alex?
D sine 30 equals 6.
Right. So we can, to get D out of the denominator here, we can multiply by D. So if we're doing the opposite operation, and here we've got 6 divided by D, here we can multiply by D. And if we multiply this side of the equation by D, we have to multiply this side of the equation by D. So now we have D times the sine of 30 degrees equals 6 miles. Okay, so now I'm already feeling relief because the D is out from underneath the fraction. But now what's the last step that we need to do in order to get D alone?
Divide by sine of 30.
That's right. So we divide by sine of 30, and whatever we do to one side of the equation, we have to do to the other. And now you can plug this into your calculator and double check that indeed the distance is 12. Making sure that your calculator is in degree mode.
Over that. Yeah, so it's
Yep.
Yeah,
yeah.
okay.
Then how does a 90-degree work?
So this is a very good question.
So you don't need
Because 90 degrees would be straight up, so what you do...
So if the plane is here, how far is the how far is the plane from the person?
6 miles.
Right.
So it would just be 6 meters.
So it would just be 6 miles, but again,
Miles, not meters.
we can also double check that using the same process. Is this B?
Yeah, but how would you make a triangle?
Well, this is a very good question. If we think about this hypotenuse rotating around the origin, one of the places that it can stop is right here at 90 degrees. When it's right here, how long is the opposite side? In other words, how tall has the height of the triangle gotten when it's right here at 90 degrees? So this is now 8. The hypotenuse is still 8. How long is the adjacent side? How wide is the base? Well, but when this is going, we can see that when this hypotenuse is rotating up, the height is getting taller. But as this point is moving here, what's happening to the base of the triangle?
It's getting smaller.
It's shrinking. You can kind of think about this like a shadow. As the sun goes up, your shadow gets smaller. And in fact, if you're at like high noon on the equator at the equinox, you have no shadow. And indeed, right here now, the adjacent side is of length 0.
Oh, okay.
So this is actually the third trick that we didn't talk about last time, but we can now actually find the trigonometric ratios of triangles that are really stretching the definition of what a triangle is. Because this is a two-sided triangle, a two-sided right triangle with two angles, like overlapping angles of 90 degrees. And a third angle of 0 degrees, and two sides of length 8 and one side of length 0. So this is really, really stretching the definition of a triangle. But we can see here, okay, if we say the distance is equal to, or we can say sine of 90 degrees is equal to 6 miles over d. We do the same
Oh, okay.
process. So d is going to be equal to 6 miles over sine of 90 degrees. Plug that into your calculator and see, do you indeed get 6 miles?
6 miles?
Yeah. Because this should be the altitude of the plane.
6, yeah. Okay.
Yeah. So this is 6 miles. So when the plane is directly overhead, it's only 6 miles away.
Okay. Thank you.
Okay? Yeah. Good. All right, other questions for me on the 4.4 assignment? Or on the additional challenge problems? Yes, Francesca.
Is there like a right triangle with 8 and negative 15? Or 8 and 15? Like, is there a known triangle or trying to do?
I feel like there is like one of the Sumerian triples.
Yeah, yeah. Or should I just do
Let's-
I'll just do math.
I think there's an
I was just trying to be lazy.
Let's not try and be lazy. But I think maybe this is one.
Yeah, let's see.
What's
Oh, yeah,
what's
that's fine.
15 squared?
That's one of them.
This is one of them.
Yeah, I have all of them right here on my notes.
Taylor has come
17,
prepared,
17.
so this is 17. That's what I thought.
There's a triple.
Is this also what you have on your list, Taylor?
Yeah, that's one.
Yeah. Okay.
8, 15, 17, 7, 24, 25, 3, 4, 5, 5, 12, 13. Those
Yes.
are the only ones that I'm aware of.
Yes,
There are more than.
there are more.
There are
Any
more.
like super big ones?
Yeah. I know that there are. I just don't. I don't have them memorized. Yes, Quinn.
I'm a little confused on 45.
On
Just like what it's asking.
41,
45.
45. Okay. So here, so this kind of relates to this last problem. So this is, although they don't make it obvious, but 225 degrees, what quadrant is that going to be in?
In the third.
It's going to be in the third quadrant. And 225 is how many degrees past 180?
45.
That's right. Meaning that this again is going to create an isosceles right triangle. Because if this angle is 45, then to add up to 180, this angle has to be 45. And if the two angles are the same measure, then that means the two legs are also the same measure.
Wow.
And so then this is basic. So this now becomes the same set of ratios as we had from this prior problem,
Okay.
because we are dealing with the isosceles right triangle again.
Great.
Another one of our usual suspects.
Okay.
Yes. Yeah. Any other questions for me from 4.4?
I have a question for my physics homework. But it's about SoControl.
Yeah. Okay. Yes.
That's why I'm asking. How do you find an angle if you have two sides? I should probably know this, but
Well, we haven't gotten there yet. We haven't gotten, but I can show you. We can fast forward ahead just a little bit. So, what are the two sides that you have?
is it in this book?
Yeah, because this one has to be 90, and this one's 45. So it's 45 plus 45.
Sorry.
No worries. You know, trigonometry is incredibly useful for physics.
Oh, I don't have it written down.
Well, let's pick. Do you have the legs or do you have the hypotenuse?
I have the
of it?
legs.
Okay.
The legs.
So let's go ahead then and pick just some lengths that we can use.
Okay, what about 8 and 15?
Okay. So 8 and 15, and from this we can calculate the hypotenuse, which is 17. But we don't really even need to do that, because do we have a trigonometric ratio that, if this is our theta,
Oh, we can use tan.
yes, we can use tangent. And so we can write the equation, here I'll create a little bit more room up here. We can say tangent of theta equals opposite over adjacent 8 over 15. Okay. We want theta, meaning theta is now the variable that we want to be alone. But right now theta is trapped inside this tangent. We need to have an operation that is the opposite of tangent. Not the reciprocal, so not cotangent, but we need an operation that is the opposite of tangent, the inverse of tangent. And on your calculator, that looks like this. To the -1 power often is notation for the inverse.
Oh, wait, is that mean
So
that,
if we take
that cotangent? I thought that meant cotangent.
cotangent is the reciprocal fraction, so we flip it. But arctangent or tangent to the -1 is actually the opposite operation. And so we can do arctangent of 8 over 15. So plug this into your calculator. Yes, Quinn.
Going back to 45, because we have all of the angles, because we don't have like a single side length to find the proportions.
You can, well, the proportions, you can pick a side length.
Okay.
But let's say that you pick, I mean, you can use the same -3 if you want to. Because remember, the proportions are independent of the size of the triangle. So if you want, you can make this -3 and this -3, and this is still going to be 3 times the square root of 2.
Oh, because it has the same proportions, it'd have the same like cosine and
Yes.
okay.
Now you just need to mind the signs. In other words, not sine and cosine, but which is positive and which is negative, because it's
Right.
in the third quadrant.
Instead of the second.
But you already have the proportions because you did them for problem 25. So then you can just use your key to check and see are they positive or negative in the third quadrant.
Oh, that's so cool.
Yeah, shortcut. All right, great job today, everybody. Enjoy your lunch. Oh no, enjoy your A-Lab and then enjoy your lunch.